All right, welcome back to Lecture 9 for Machine Learning. This is Machine Learning 2, actually. Um, so today we're going to start working on the concept of sampling. So, okay, the US population is approximately 315 million people as of the year 2013. Now, if we want to find the average height, we all know how to find averages. We just find the entire 315 million people, add them together, right, and average them together. So this is how we find the average. Of course, it will be very difficult to do that. So what we normally do is instead of averaging, we just pick a subset of the population. Instead of 315 million, maybe we'll just pick 10,000. And using the average of this 10,000, we are hoping that the average of the 10,000 is approximately, this is the symbol, this is a symbol for approximately, will be approximately the same as if you had used the entire 315 million. Now, the reason why we can do that is through this concept called law of large numbers. And given the definition of an average, so the average is essentially you add them up and divide by the number. So that's average. The law of large number basically says that as the as the number of sample increase towards infinity. So as you gather more and more and more sample, the probability the probability that there's a big difference. So this is the true average, and this is the average that you calculated, right? So this is yours, and this is the true. Therefore, the difference between them is the error. So it's saying that the probability is of the error is bigger than some number approaches zero, and that number could be any number. So this number could be like 0.000000000, like very tiny. So what it's saying that as you gather more and more and more samples, the probability of the error approaches essentially zero, right? The probability that the error is greater than some number would be zero. So, this tells you that just by taking average, if you take a large enough number of average, then this probability, then the chance that your error is very, very small is very high. Well, approaches 100%. So this is the reason why we don't need the entire 315 million. Instead, 10,000 probably would do the trick. Okay. Now, the law of large numbers, what we just learned, leads to a very, very special conclusion. Okay? The conclusion is if we have the data, so far we learned from the data, we've spent a lot of time learning this function, p of x. From the data, we can get a function. Now, once we have the function, we can find the expectation. So the equation for the expectation is the integral of x times px. So last class we went over why that's the case. Now we can also calculate variance, which would be the distance from the center square. So you're finding the average of distance from the center square times x. So given data, this is what we could do. This pipeline, right? We've seen this pipeline, and all of these integrals can be done once you have p of x. So we know p of x, and we can calculate whatever we need. The large number give us the special conclusion that from the data, instead of getting p of x, right, we can still get the mean. We can get the mean simply by averaging, the number. So if we just average this, then this would be an x bar, and the error between them should be pretty small if you have a large enough number. Similarly, if you have the data, you can just find the average distance square from the center, and by averaging them together, that should also give you the variance. So, so this implies that we can calculate this integral, which is the expectation integral, using averaging. We can calculate the variance integral with averaging. We can also calculate basically any function, right? So notice the p of x here, p of x, p of basically any function of the integral given a p of x with averaging. So the key observation here is that integration sucks. Averaging is easy. So if you have a large enough number, you can avoid the integration, right? Avoid it and simply do the averaging. Okay. And averaging in many, many ways is just a lot easier and it does a pretty good job. So this leads us to conclude that any integral containing p of x, see, any integral containing a p of x can be approximated by averaging. And the step goes as follows. You first convert the integration into summation, right? Notice the integration becomes summation. Integration, summation, integration. So that's step one. Once you converted that, you remove p of x. So p of x is gone, right? So notice there are no p of x here. And right after that, you average all the samples from p of x. So you after that, you just basically plug whatever sample you have, and then you essentially will average them together. And the result, the final result, reflects the original integral you were working on. Now, let's continue with this idea. All right. So, your first exercise. Let's pretend Professor Wu has some kind of supplement that can speed up the brain's processing power. Okay, so it makes you think faster. And as a side effect of this, your perceptions of time, x, changes to 2x. So this means that while an average person perceive 1 second, so they feel like 1 second has passed, people on the supplement will feel like 1 times 2 plus 1, which is 3 seconds. So time is a lot slower for these people because they're thinking a lot faster. Okay. So if that's the case, load the lunch wait time. So let's say this is the lunch wait time we've done in the past. And you should by now have the p of x. Okay. So if you have the p of x, now find the expected wait time. So you can essentially solve the integral. So you can solve after you solve the integral, if you were to solve the expected x just by taking the average, okay? So the averaging should do a good job of approximating an integral. This averaging should give you a good job. Okay, so that's the first thing. All right, if you can do that, the next goal is okay. Professor Wu is using this supplement. Okay, find the expected wait time f of x from Professor Wu's perspective by solving this integral, right? So now, previously it's x. Now, we are not looking at an average person's wait time. What if a person is on the supplement and their perception of time changes? So now it's and this function follows 2x plus 1. So now you need to solve this integral, right? To solve this integral, you can basically approximate it by simply averaging these results together. Yeah? So you would essentially generate your samples from the exponential, and once you generate the samples from uh, take the samples from the exponential, and you just do the averaging. That should give you a very, very similar result as the integral. So the integral and the averaging should be the same, okay? Which is stated here. Did the averaging do a good job? Okay, so pause the video. Make sure you can do this. You can always check your result with my solution here, but ideally you want to think through and try to do it yourself. Okay, pause the video. I'm going to move on. So the power of using averaging for integral requires that you have samples. You must have samples. If you have the samples, then you can just do averaging and get the results. Now, solving integral with averaging assumes you have samples, right? You have samples to average. But what if you don't have any samples? Can you still solve very complicated integrals that look like this? X should not be there. Can you still solve very complicated integrals by averaging? And the answer is yes. Yes, you can still approximate integrals this way. If you only have the equation and you don't have the data, what you can do is you can generate your own data from the equation. So previously we have data, right? And then from data, we're able to find the equation. And now we have the equation and we don't have the data. And we're saying that you can generate the data yourself. Okay? So this process of generating your own data is called sampling. And there are many, many ways to do sampling. We'll learn the simplest way, which I highlighted in red. So these are the simplest ways to do sampling. The blue ones are much more advanced, and they make more sense to be taught in a more advanced setting. But we got to start somewhere, so this is where we're going to start. So sampling is the generation of data from a distribution. So let's say with Python, you can generate a normal. Normal is the same as Gaussian distribution with some kind of mean and standard deviation. And I'm saying that I want to generate 10,000 of them. So n, I want to generate 10,000 of them. And after you generate them, if you look at a couple samples, you can't tell. You can't tell that these samples are samples that would form a Gaussian distribution, right? If just by looking at 10 of them. However, if you were to plot out the histogram of the entire thousand samples, you end up getting something that look like this. Notice how this is a Gaussian distribution centered around zero, right, with a standard deviation of one. So, so if this is the case, this Python code essentially allows you to generate the samples. Okay, and you will see that this is right here. The distribution actually have a mean of zero and the standard deviation one. Okay, so this assumes that we have p of x. Once we have p of x, we generate the samples, right? Samples. From the samples, if we take the mean and the standard, we actually calculate the average as well as calculate the average distance from the center square. Then this constitutes the approximate mean and the approximate standard deviation. So notice how the approximate mean is pretty close to zero, and the approximate standard deviation is pretty close to one, close enough to one. Okay. So from here, from P of X, we generated data. Then we use the data to essentially identify the expectation and the variance. Okay. So I think I talked about this already. So sampling from simple data. So if we are sampling from really, really simple data, you probably can just use NumPy and Python, right? For really simple ones. However, many, many useful distributions in life are not the standard ones that we have seen. And when that's the case, you need to learn alternative approaches to sampling. Assuming that you can sample from simpler ones, how can you then sample more difficult distributions? So the way you can sample from difficult distributions would be these are the different ways: inversion sampling, importance sampling, rejection sampling. There's more than these, but these are some of the easiest ones. Another time, when you get to more advanced, then you'll learn probably Gibbs sampling, MCMC, Metropolis Hastings. The flow model is pretty good too. So these are the more advanced ways than you'll run into. Okay. So like I said, with just simple distributions that we are familiar with, you can just use Python, right? So for exponential, you can just call this command. It will generate the exponential for you, right? And then categorical, right? You can just generate categorical. right? You can generate a Gaussian distribution, also called normal, uniform, Poisson. All these are simple distributions. And if you just want to generate the distribution, then uh, Python allows you to do it. Just as I did here, right? I generate a Gaussian distribution using the command normal. And after I generate that, you can see that the data reflects the distribution. Okay, there's a there's a full list if you want to click on this link. So the problem comes, like I said, problem comes. What if we encounter a non-regular distribution? So the point of today's class is not not for you to be able to generate these, but for you to generate more difficult ones. Okay, so when they're non-regular distributions, then what do we do with those? Okay? So the easiest one, the easiest approach that most statisticians learn is called an inversion sampling. So you may remember the function CDF, right? CDF. Now, when you put x, a value inside CDF, like 1, for example, what CDF returns is the area. Okay. And if you plot the CDF out, right, as you head towards more and more larger number, it's adding towards 1, right? So because the whole probability is 1. So eventually you'll reach this this point and your entire area will be basically 1. That's why the CDF heads towards 1. Therefore, the output of a CDF is always a value between 0 and 1. Okay? This means that if you were to sample a distribution between 0 and 1, so uniform distribution, then then so let's say this is exponential, right? This is the CDF of exponential. So if you were to generate a random value v, and then solve for x, x would then be the value here. Okay, so let me say that again. So this is a CDF plot, right? It adds up towards 1. This means that if you generate a value between 0 and 1, like here, for example, 0.7, right? Now, if you've given that you have, we'll call this V, given that we have V, we can solve for the corresponding X value. And if we solve the corresponding X value, the X value would be the sample that would have generated V, which means that every single time to generate a sample, all we have to do is randomly generate a value between 0 and 1. Once we generate that value, we plug it into the inverse CDF of whatever distribution you want. So here is exponential. So if you want to generate exponential, then we plug V in here and then solve for X. Once we have X, that is a single sample. We do this again, generate another V, and then solve for X again. That would be the second sample. And we will repeat this, right? And you will essentially be able to use this by generating random uniform distributions. You will be able to generate other distributions out of it. Okay. So this is the inversion sampling, where for over here, this right here is the CDF. And if we sample V, this means that we plug V here and then we solve X. If we solve for X, we end up getting this relationship. Therefore, if we all we have to do is generate bunch of V's from uniform distribution. By following through this equation, this will give us the corresponding samples that would be the exponential. That would be the exponential distribution. Okay. So, okay, hopefully you got that idea. So you'll practice, you're going to practice inversion sampling. So write the code that uses inversion sampling to generate an exponential distribution. So your goal is to generate exponential distribution. First, generate sample from a uniform. Remember, I generate a bunch of uniform distribution. According to inversion sampling, if you plug your samples from uniform into this equation, because we calculate the inverse. This will be your samples for the exponential, right? So these samples should be exponential. Plot the histogram and show that indeed it is exponential. Then calculate the mean and generate the samples. Show that it has the correct mu. Okay, so this is your next exercise. The solution is right here. It basically, if you were to just generate uniform like everything I talk about, notice how you did end up generating a exponential distribution. Okay, all right. Using only p of x and no data, we can approximate the expectation. Right? We can not only expectation, we can approximate any function with that p of x. So then this is yet another exercise. If you finish the previous one, you can start working on this one. So given an exponential distribution, so let's say you have an exponential distribution, you want to set the theta to 0.5. Therefore, we know that the averaging is 2, right? Since we don't have any data, you are going to generate your own exponential distribution. Once you generated your own exponential distribution, you will be able to uh, calculate the averaging. Right? Once you generate your own, you can find the average, and you can see that the average, that you get is should be approximately 2. So the purpose of this exercise is basically to convince you that if you only have p of x and no data, you can generate your own data and still uh, 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 approximate the integral. Okay, so this is another exercise. You want to try to do this. Okay, I think this is very similar, right? This is no, yeah. This one is inversion. This one here is to convince you that if you don't have data. All right. I also provide the answer for you here, so you can take a look. Rejection sampling. Okay, the next one is called rejection sampling. Rejection sampling, it's used for distributions. Once again, it's used for distributions that are not common. If you want to pick a common distribution, so if you want to sample from P of x, what we do is we pick a distribution Q of x. So this is P of x, and this is Q of x. And then we multiply Q of x by some large number. So K. We multiply Q of x just enough so that Q of x is always larger than P of x. Okay? So that K times Q is always larger. With rejection sampling, you're going to sample from Q and call this mu. So what you do is you're going to sample from this Q distribution, like here. Once you get a sample, we're going to call this particular sample mu. And then we're going to sample a uniform distribution between here and here. So let's say this is 0.1, right? We're going to sample a value here. And we're going to call this value V. So that's V. If V is greater than P of U, so if this value V is greater than P of U, which is right here. I should have picked another one. This is not as obvious. Let me zoom in here. Let's zoom in and let me change the pen. Okay, so let's go over the step one more time. What you do is you first generate a sample using Q. So this is Q of X, right? So once you use Q of X, and let's say you generate a sample right here. I think this is 1.5. So you generate a sample. We're going to call this sample U, okay? From U, you're going to draw a line here, okay? This point is K times QU. And then Once you have k times qu, you're going to pick a point between here and here uniformly. You pick a uniform distribution in between. So let's say you pick this value here. This value here. Now, if this value, and then the point where it intersects this, we're going to call it P of u. So this value here, we're going to call it, what are we going to call this value? V. Okay, so that's V. So these are the steps. Once you have V and P of u, if V is greater than P of u, then this sample here you're going to reject. However, if V is less than P of u, then you're going to accept. If you reject it, you just start the whole process again. If you accept it, it means that you're going to keep this sample as your first sample. That's what that means. Okay, call this V. If the probability pick, yeah, probability we'll accept is P times U divided by Q times U. Okay, so that is the steps to do this, to do the rejection sampling. Let's see if we can go over again. You sample from Q. Once you sample from Q, like we're going to call that value U, so that's step one. And then you sample again between 0 to KQU. So between these 2 points. The resulting sample, we're going to call it V. If V is greater than PU, you reject. If V is less than PU, then you accept. Now, the reason why this works is because the probability that you will pick this point, U, right, is Q of U. Now, then the probability that you would essentially accept is K times Q of U and then P of U. So when you have both conditions, you multiply them together, they cancel out, and this gives you P of U times 1 over K. So the end result is you will end up generating a sample that's under the curve, which is P of X. Okay. Rejection sampling, it's something that you actually have to you have to follow the steps and think about why it works for a while. So don't be discouraged. Rejection sampling is not easy. Okay. Rejection sampling. Now, you might be wondering, some of you who's following along might be wondering, in the end, you're going to generate distribution, and it's P of U, but it's P of U divided by K. Well, is that the same as P of U? Well, the answer is yes. Let's say you have P of U divided by K, right? Let's say we have a Bernoulli. So the distribution where the probability is 0.5 and 0.5. Now, if you were to divide, let's say we have a K of 2, therefore now the probability is going to be 0.25, 0.25. When you draw the histogram out, notice how it's going to rebalance itself to be 50-50. So it doesn't really matter. Okay, so sampling. So we've been talking about various sampling. We did the inversion, and then we did the rejection sampling, right? Now, sampling is how some of the, actually all of the, how the generative models work. And the way you can understand how this works is through this strategy. This is not the exact strategy, but it's something that can give you a general idea of how it works. Let's assume we can generate a bunch of data from a Gaussian distribution. Okay, so we have a Gaussian, we can generate this data. So we can sample it, and we're going to call this x. Now, if we pass x through some kind of function, we're going to call the output of this z. So this data has a probability distribution of z. Okay, and now we have another data set with pictures of people. So this is pic of people, and we're going to call this y. And then distribution. So this distribution, right? This data set consists of pictures of people. Therefore, the probability distribution is a probability distribution that describes like people as well. Um, if this is the case, then every single sample in here will be a single picture of a person. Okay, which is the case because that's our data. Now we have P of z and P of y. Well, what will happen if we can find a distance between them? So we want the distance between them. So if the distance between them is 0, it means the two distributions are the same. And if the distance between them is very large, it means they're very, very different. And we're going to call this way of measuring distance between them the KL divergence, KL. So KL divergence is going to measure the distance between these two distributions. Now, what would happen if we were to find the function such that P of z and P of y distance as small as possible? Like, you want to take a second and think about it. When this happens, basically, you are saying that P of z has the same distribution as P of y. And remember, every sample in here is a picture of a person. Therefore, if you can find a function such that P of z is the same distribution in P of y, then every single sample in z is also a picture of a person. So this has like really incredible implications. So this means that let's say you have data, right? So you're generating random data, and you're going to pass it through a function, and then the output of this is P of z, right? It's going to be data z. So every single sample in here, if this is equivalent to P of y, then every sample here is a picture of a person. This implies that you can randomly generate some data from a Gaussian. And as long as you know the function, you pass it through the function, then output is a picture of a person. All right. So this is how the generative model works if you want to generate like a picture of a person. I mean, there's a lot more detail than this, but you can get the gist. Is that you're trying to find a function such that the distributional difference between them are minimized. Okay, so if you can then do that, then you generate like I said, you simply randomly generate a sample from Gaussian, and then you would be able to map it to a picture. Okay, so over here's some website. There's a website that I think called Lexica. I don't know if they use the exact approach I just described, but I know they definitely generate samples. So these are the samples that they generated. Like this is a picture of a face, right? Here's two people here, or they even learn how to generate anime, animals, cats, really really cute chipmunk, right? Some more faces, more faces, more faces, the universe. So you can see that the power to generate samples is basically like underneath the foundation of how these generative models work. Okay, there's one more a technique called important sampling. This is when this in this particular case you're not generating samples. You're focusing on finding the integral. So let's say you have a distribution like this, right? And you want to sample it. And normally you simply sample from P of x if you can. In this particular case, you can't sample from P of x, but you know how to sample from Q of x, which means that if you just multiply Q of x and divide by Q of x, then you now can just convert all of them into a single equation. So that's just G of x. So now you can essentially generate samples from Q of x, and then w- perform the averaging on G of x. Right. So this is just a technique that allows you to solve integrals better. Okay. KDE sampling. All right, let's quickly go over KDE sampling. So KDE sampling, step one, you essentially pick a sample from your data because KDE requires that you have the samples, unfortunately. So you do you oh for KDE sampling, you have to have the samples, which is kind of funny. You already have the samples, then why do you need to sample more? I don't know. But anyway, so this is KDE sample. You pick a sample. Let let's say this sample is we're gonna call this sample x1. We're gonna let x1 be the center. So x1 is going to be the the mean of a Gaussian distribution. So you're gonna have a Gaussian distribution x1, okay, square 2 sigma square. So and then once you have this Gaussian distribution, you're going to sample from this Gaussian distribution where mean is equal to 1. You can pick the variance, just like when we do KDE, you pick the standard deviation here. Like if depending on the number you pick, smaller number will be sharper, larger numbers will be smoother. And that's it. That's it. You pick you once you have a Gaussian distribution, you generate a sample, we'll call it y1. That's your first sample. Once again, you pick another sample. We'll call it x2. We'll let x2 be the mean of a Gaussian. Then you sample from the Gaussian. Then that's your y2. That's how you generate KDE samples. Okay. All right. In summary, sampling allows you to generate sample from P of x. Right. It could be distribution of faces, distribution of speeches. Right. You can just have it produce a speech. It could be distributions of artwork, music. You can have randomly sample and it'll give you a song, for example. Or you can use it to solve very difficult integrals with averaging. So sampling is a really, really powerful technique. Okay? All right. Use sampling to solve an integral. So over here, this is an integral. Let's see. Over here, yes. So let's say we want to solve this integral, right? It's only f of x. There's no p of x. However, there is an implicit p of x because between the range of 0 and 2, there is a uniform distribution, right? 1, 2, 1 half. So a uniform distribution between 0 and 2 is 1 half. So we can simply multiply 2 and divide by 2, where this right here is the uniform distribution. Once you have the uniform distribution, P of x, right? You have P of x. Now you can get rid of P of x. You can get rid of it while keeping the 2. Once you keep the 2, P of x, remember the steps. You convert the integral into sum, and then you get rid of P of x, and then you just average it up. This result will basically solve the integral for you. Okay? All right. For your first practice, see if you can solve this integral. Your next practice, you will need to solve, let's see. Yeah, this is the solution actually for this. Write the samples. For the next one, see if you can solve this. This is not as straightforward. You might notice that 2e to the minus 2x is an exponential distribution. Exponential. So you think you should be able to sample from exponential, except you need to like pay a little bit more attention because exponential goes from 0 to infinity. Okay? All right, so I also provide a solution for you here. Let's see. This is the last exercise. Once you're done, do this one as well. And I think that's it. That's it. Okay. All right, good luck.